Okay, so hopefully the last lecture on PN junction. We've already spent too much time. This is the eighth lecture on PN junctions, and the reason why we have done that so many lectures on PN junction because first of all, it's very important, and then it's a simple enough device through which you can illustrate a lot of important concepts associated with devices. If I take a more complicated device, things become more difficult. Okay, so it's a good illustrative example. All right, so today's lecture would be on dynamic characteristics of PN junction. So far, we have looked at PN junction under steady state, which means basically DC condition. When you have a steady state voltage applied and a steady state current is flowing, we have looked at PN junction characteristics under those conditions. So today we look at how PN junction behaves under time varying conditions. Okay, so dynamic in that sense, time varying. All right, so we have seen that if you take a PN junction diode, you apply a voltage here, then in forward bias, you get a current which is given by this term here, which is due to diffusion and recombination outside the depletion region, and you get a term here which is due to recombination within the depletion region here. Now we know that this, of course, is an under steady state or DC condition. Now, if I make voltage, let's say time varying, then in addition to conduction current, which we are all familiar, in addition to that, there would be a displacement current. Displacement current, we know it comes about because of charge and discharge of capacitances which are there. So in addition to conduction current, this is like a conduction current, we would get a displacement current. All right. And so J would be, as a very simple approach, J would be equal to whatever conduction current is flowing plus a current which comes about because of charging and discharging of capacitances. And therefore, what we expect is that in addition to this current that we derive, now, I've removed the recombination part here. We're looking at higher forward biases where that is not critical. And so in addition to conduction current, we get a current which is displacement current, which is equal to the rate of change of charge with respect to time. So what we are saying is that a PN junction operates when you apply a voltage, certain charges are injected into, certain charges are there inside the depletion region. Certain charges are there inside the PN junction. And as you change the voltage, the charges have to increase. If you reduce the voltage, charges decrease. And therefore, there is a current component that comes in, which has to supply that particular charge here, del Q by del T. And so now, throughout the discussion, the assumption that we will be making, an assumption of quasi-static assumption here. So we are looking at transient, but we are looking at transient. For example, if we look at it, the current we have written as a function of voltage. What we are saying is that as long as a certain voltage is there across a PN junction, the current will be obeyed by this particular equation there, right? The conduction current. But then this current, if you go back and look into the derivation, the current has been obtained through solution of continuity equation. And when you solve continuity equation, remember you get excess hole density, excess electron density, and from there you get this particular value of current. But how did we get the excess hole density and excess electron density? We got it through continuity equation. And in continuity equation, we said del P by del T equal to 0. And that's how we got it. But now that we know that we are in the transient condition, del P by del T is no longer 0. And therefore, if this is no longer 0, then the hole density profile and the electron density profile is not going to be the same as steady state condition. So the profiles will change, and therefore the current expression also changes. But what we are saying is those changes are small, and we can think of transient also, transient condition being very close to the static condition here. And we call this as a quasi-static assumption. Later on, if I have time, I'll provide a more rigorous definition of what this assumption is and under what conditions it will be true. Okay. So what we are assuming then is, even though continuity equation is like this, we are saying that this term is not very large. Not del P by del T is not very large. Okay. And therefore, the distortion caused by del P by del T in the carrier profiles is not large here. So I can continue to assume, for example, that the carrier density goes as exponential here and exponential here, and therefore this current is valid. Okay, so that's like a quasi-static assumption. We are saying the transient condition is not very far from static condition. We are close to that kind here. So, and so we have this current, and in addition to that, then what we are saying is we get a current due to you have to charge and discharge the capacitances which are there here. Okay, so what we need to do is to find out what the current is under transient condition. This current, of course, is there. We need to identify what are the charges. Where are the charges present in my PN junction? Q here. And once we can identify the charges here, and then we have to find out how they change with voltage, and we can figure out then what this contribution is. All right. So what we need to do is del Q by del T that we see here. In general, the charges inside the device would be several distinct components. For example, one can see already that I have a depletion charge. So Q1 may be the depletion charge there. Plus, we know that we have excess holes here. So we may have Q2, which is excess holes here. Plus, we may have excess electrons here. So I may have another term Q3, which is excess electrons here. So in general, what I have to do is identify what are the different charges that are there inside my device here. And for each one of those charges, you have to supply those charges under transient condition. They increase or decrease. So there's a current component, right? So we have to identify them, and then they will give rise to a current component here. So the task is then identifying all the charges. And remember, if I look at a charge, let's say del Q1 by del T, I can obviously write del Q by del T as del Q1 by del V and del V by del T. And similarly, del Q2 by del T here, del Q2 by del V into del V by del T here. So what you're seeing here is that this displacement current obviously is equal to a capacitance times del V by del T. We know displacement current is C dV by dt. So that's what it is. So corresponding to each charge, Q1, there would be a capacitance C1. Corresponding to another distinct charge, Q2, there will be a capacitance C2, and so on and so forth here. All right. So this total current in a PN junction would be conduction current plus this current here. And this current here then becomes C1 del V by del T, C2 del V by del T, and so on and so forth. So the transient characteristics then we are saying is nothing but a steady state component, plus we have to find out what the capacitances are in your device. And once you know the capacitance is C1, then you just multiply by the derivative of voltage with respect to time, and similarly you get the extra current that you get under transient condition. Okay, so that's the approach that we are taking. So the whole thing boils down to identifying the charges Q1, Q2, and so on and so forth, taking the derivative and writing what the capacitances are C1 and C2 and so on and so forth. Okay. All right. So that's what we need to do. So the model then that we have is for a PN junction. Now note, under transient conditions, we have this current, the first current, the conduction current, which we represent by a current source because it's voltage dependent. So we have put a voltage dependent current source, I naught. And of course, it depends on the voltage across it only. Okay, so I naught is this current here. And in addition to that, we are saying under transient condition, we would have a current due to a capacitance C1. We have to find out what it is. So we put a capacitance here, and a capacitance C2. So we put it here. Because the currents are adding up, that's why we put them in parallel. So I have I naught plus C1 dV by dt. So it's in parallel here. C2 dV by dt. So this is also in parallel here. If I have another capacitance C3, we would also put it in parallel. So a diode then, under transient conditions, is not just this current, but a capacitance is in parallel. Okay, C1, C2, C3, and so forth. This, of course, refers to this component. All right, so let's identify then the different capacitances that are there: C1, C2, C3, and C4. Okay. All right. So, okay. So now here is a PN junction, and the first thing that we know is that there is a depletion charge, right? As we said, we have to identify different charges which are there. So we know that there is a depletion charge. Depletion charge is over here. Okay. And we know that there is a voltage applied and depletion width is of a certain magnitude. If I increase the voltage, what will happen? If I apply forward bias, increase the voltage, depletion width shrinks. So now note that it will shrink here, right? It shrinks. Now when it shrinks, the depletion width, what do you have to do? Note that at this point, there was a depletion region, right? Earlier, depletion region means that there was ionized acceptor atoms. Now this region has now gone away. So to do that, what do you have to do? You have to supply holes. The holes have come in and they have neutralized this particular region here, right? Holes have come in and they've neutralized this region here. Similarly, electrons have come in, and the ionized donor atoms that were there, they've been neutralized by the electrons that come in. And therefore, you can see that I have a current component which is coming in to supply the change in the charge here. As the depletion width changes, well, I have to supply a current here. So this is the current that we are talking about, right? So del Q by del T, how much charge do I have to supply? Well, del Q by del T equal to minus del Qj by del T, right? Qj is the junction charge here or the charge here. Now, as the charge shrinks, then I have to supply the charge here, right? So del Q by del T, the charge which is coming in from here, is equal to minus del Qj by del T. As the junction charge decreases, I have to supply charge from here, okay? And therefore, one of the charges that we have identified is the junction charge here. And then this charge del Qj by del T, we can write as del Qj by del Vj into del Vj by del T. Vj is nothing but the voltage across the junction, which is nothing but the applied voltage here. Okay, I've just used the terminology Vj here, but note that Vj is same as the applied voltage here. So, all right, so we define Cj then as minus del Qj by del Vj is the junction capacitance. Note that as you can see that the capacitance is positive because as voltage across the junction increases, the junction charge decreases here. That's why the minus here, and Cj is minus del Qj by del Vj here. And therefore, what we have identified is one capacitance inside my PN junction, which is the junction capacitance, which comes about, we also call it the depletion capacitance, which comes about because of change in depletion charge with change in voltage here. And this is something that we have already done before when we have a PN junction with abrupt PN junction here. This is the depletion region on the N side, depletion region on the P side here. And we've already obtained Xn and Xp and Vbi minus Vj. All these equations we've already obtained. So junction charge or depletion charge, we know total charge will be equal to Q times Nd times Xn. I can take it either on this side or that side, is the same. So Q Nd Xn. Xn is given here, W Na by Na plus Nd. So we get this term here, total junction charge. And W, note that W can be expressed in terms of Vbi minus Vj here. So we can get a total junction charge in terms of the applied voltage here. So these are equations that we've already derived. So we are just putting it together to calculate the net junction charge. Now all I need to do is take its derivative with respect to Vj here, and therefore we get a capacitance. Please note that all these charges that we have are charges per unit area. So capacitance also that we get is per unit area. So total capacitance would be the total junction area multiplied by this term here. So we have obtained an expression for total junction capacitance, which is over here. And so this is the expression. Note that what we can do is we can write it Cj as some Cj0 divided by, so we can write it as the junction capacitance at zero bias divided by square root 1 minus Vj by Vbi here, and junction capacitance at zero bias then is given over here. Alright, so we have obtained an expression for junction capacitance as a function of the applied voltage here. And the zero bias capacitance depends on several factors here, depends on doping, depends on built-in voltage. And in general, this is for an abrupt junction, PN junction. In general, what we can do is we can take this equation and generalize it and say Cj is equal to Cj0. In general, 1 minus Vj by Vbi raised to the power m. And m is what we call as the grading coefficient. It depends on the doping profile. For the case that we are looking at, where we have abrupt change in doping from p-type to n-type, we have seen that m equal to half here. If you have a different doping profile, you don't get this expression for capacitance. You have to redo the Poisson equation solution, and you find that m is in general different. Okay. All right. So m equal to 0.5 for abrupt junction, and one can show that so abrupt junction is like this here. Doping abruptly changes from Nd to Na, and doping is uniform in this region. Doping is uniform in this region. So for that case, we have derived m equal to 0.5. On the other hand, if you have a linearly graded junction, linearly graded, which means the doping is varying linearly here. All right, so the doping is varying linearly. This is showing the space charge region here, so which shows that the charge changes linearly with x, and then of course charge falls to 0 because that's the end of space charge region here. Charge falls to 0 here. If you have something like this, then one can show that m equal to 1 by 3. It's not hard. One can do an analytical solution when you have things changing linearly, and one can show m equal to 1 by 3 here. So the point is, junction capacitance in general is zero bias capacitance, 1 minus Vj by Vbi raised to the power m, and m will change depending on the doping profile in these regions here. Okay, and m equal to 0.5 for our case here. All right. The other thing is, note that this expression that we have derived, and we have this expression for W, one can easily show through these two that Cj is nothing but epsilon s by W here. So, although this is a complicated expression, but the junction capacitance is like a parallel plate capacitance here, with the distance between the two plates equal to W here, and one can see why. As I said, if I earlier had a depletion width like this, depletion region, and I apply an excess bias here, the depletion width shrinks, and what has happened is the holes have come here and neutralized the acceptor atoms here. The electrons have come here and neutralized the donor atoms here. Where have those charges come? The charges are here, and the charges are here. Those are the charges that have come from the external circuit. And what is the separation between the two charges? It is W here. So one can see a parallel plate concept here, right? The charges came in and they're sitting here, and the charges came in and they're sitting here. And the separation between the two charges is W here, and that's why it acts like a parallel plate capacitor. Okay? Except that, note that these positive charges will be compensated by negative acceptor atoms. And similarly, the negative charges here will be compensated by positive donor atoms here. These are the charges that came in from the contact here. And these are the charges that came in from the contact. So the charges that come in, they are sitting here, and they are separated by a distance W. And so that's why junction capacitance is Vs by W. All right. So it's interesting now. So we have obtained a expression for junction capacitance here. Now, for a moment, if I go into reverse bias, in reverse bias, we said that the general model for a PN junction is going to be the current in parallel with C1, C2, the different capacitances that are there. Now, in a reverse bias, I don't have any current, negligible current, and I don't have any other charges. Because if you look at a PN junction, when you apply a reverse bias, the only charge is a depletion charge. And after that, there are no excess electrons or holes, or they are negligible. There are no excess electrons and holes here. So you have no other charges, no other significant charges. The only charge that is there in a PN junction under reverse bias is this depletion charge. And therefore, you have only one capacitance, which is the depletion capacitance, which we have calculated here. There's no other charge there. Okay. And therefore, in reverse bias, if I neglect, I have only one capacitance, depletion capacitance. And if I neglect the current here, leakage current, or which is very small, then reverse bias diode is nothing but a capacitance. That's what it is. So a simple way of looking upon a reverse bias diode, when you are away from breakdown, then it's simply a capacitance here. And note that it's a capacitor whose value varies with the voltage. So it's a variable capacitor, and we have a name for it. We call it Varactor. So capacitance whose value you can alter by altering the voltage here, and you can see it here, right? So Cj you can alter by changing the voltage applied here. So that's a very useful property. And Varactor is a diode, PN junction diode and a reverse bias, and you can go and commercially buy these things. Anytime you have a capacitance which changes with voltage, and you know that, for example, if you have an oscillator, the oscillator's frequency usually will be 1 over R times C. And therefore, C is something that you can change with voltage. And therefore, it allows electrical tuning of frequencies and things like that. So that's a very useful property. And Varactor diodes are there. You can buy commercially in the market. Let me give you an example. You do a Google search, you'll find many Varactor diodes. So randomly, I've picked one. So here is a Varactor diode. And note, when they're advertising this Varactor diode, they're advertising for VCO, voltage control oscillator. You can change its frequency with voltage. And they list several things. As I said, it operates under reverse bias. So they're listing the reverse bias current here, 50 nanoamperes. And they list here CR equal to 6, which basically means the ratio of capacitance when you apply, let's say, this is not come, when you go from 1 volt to 6 volt, or 1 volt to 7 volt, right? What is the change in capacitance? When we are talking about a Varactor diode, we would like capacitance to change rapidly with voltage here. We would like it to have high sensitivity. So CR is, they're saying you can get a factor of 6 change in capacitance here. And note, when you're using a PN junction diode as a Varactor, this is the symbol that you use here. You have a diode and you put a capacitor at the end here, right? So it's being used as a capacitor, variable capacitor here. And I don't know if you can see this graph very well here. It starts off with a value of around 5 picofarad here. This capacitance here, 5 picofarad. And at around 6 volt, 50 picofarad here. So at this point is 50 picofarad. And around 6 volt, it falls to around 5 picofarad here. 5 picofarad here. So from 50 to 5, right? From 50 to 5 as you go from 0 to 6 volt here. So quite a bit of change here. There's a factor of 10 change, right? And which we will not get by our method, right? In our case, Cj goes as square root Vj here. So if you change by a factor of 10 the voltage, even if you neglect, let's say you have reverse bias, so you have plus Vr, and if you change by a factor of 10, what will you get? Change by a factor of square root 10, which is a factor of 3, right? Which is a factor of 3. These guys are getting a factor of 10 change. 10 change in capacitance here, which means what? It's not this kind of a diode here. Not an abrupt junction diode here. So the whole point in a Varactor diode is, what kind of a doping profile should I choose? So doping profiles are very carefully chosen in order to maximize how capacitance, the sensitivity of capacitance to voltage. Okay, so that's where one needs to focus. I'm not going to go into the details here. So what doping profile allows you to get a maximum sensitivity of C to Vj? So in their case, of course, they have a fairly sensitive capacitance here, which is varying with voltage here. All right, so don't expect them to be abrupt junction. These are not abrupt junction diodes. They have a more complicated profile. All right, so another thing about this capacitance before we leave it, if you look at Cj, one can, for an abrupt junction, Cj is here. One can take 1 over Cj square. And interestingly, 1 over Cj square, if you write it out, you find that it linearly changes with voltage here. Linearly changes with voltage. And capacitance is very easy to measure. As we said in a Schottky diode, capacitance in a PN junction diode, you can measure it. And if you plot Cj, 1 over Cj square versus Vj, you'll get a straight line. And then you get interesting things here. So all that you need to do is take a PN junction diode, measure its capacitance as a function of voltage, 1 over Cj square. And if it is a abrupt junction diode, then you have a square root manner here and you will get a straight line. If it's an abrupt junction. If it is not an abrupt junction, you will not get a straight line, 1 over Cj square. So that's another signature. Because remember, we said Cj for a linearly graded, it would be not square root, but it would be 1/3 cube root. Okay. But if it's a abrupt junction, 1 over Cj square, you'll get a straight line. And if you extrapolate it, well, you can get VBI. The built-in voltage you can experimentally measure. And if you look at the slope will give you this part here, 2 by Qs, Na, Nd, and Na here. And 2 by Qs, of course, you know. So therefore, you are able to determine this particular part here. Na plus Nd divided by NdNn. Many times, what we do is we make a diode which is P plus N. And when we make P plus N, Na becomes very large. So Na cancels here. And this term is practically equal to Nd. And therefore, you can measure the doping. The doping of the lightly doped side here. Na cancels and you get Nd here. And you're able to measure the doping from the slope here. So capacitance versus voltage characteristics are very commonly used as a characterization method to measure VBI, to measure doping. And the origin is this particular expression here. All right. Things are more interesting in forward bias. In reverse bias, then we only have a capacitance. But in forward bias now, we know that when we forward bias, besides the depletion region changing, we have holes which are injected here. And we have electrons which have been injected from this side. So we have more charges, right? We know this here. Delta Px here. And we have delta Nx here. But then note that this region is neutral. This region is neutral. right? Which means what? I have delta Px, excess holes here, but along with excess holes, what do I have? Excess electrons also. They're all there in this particular region here. Similarly, I have excess electrons here, but along with that, I have excess holes also. And the overall region is neutral. But I have charge, okay? I have charge here. And under sort of quasi-static approximation, we know how these charges go. They go like this here. Exponential Ni square over Nd exponent QV by Kt minus 1. That's the excess hole density here. And then this is how it decreases exponentially with the diffusion length. So this we have derived, but again we have derived under steady state condition. Under transient condition, we are making an approximation of quasi-static to say that this is still true. It may not be true. Strictly speaking, it's not true. There are deviations from this kind of a profile. All right. So we can calculate then what is the excess hole charge. If we know excess hole density as it goes here, I can take the excess hole charge, which I can take Q times delta Pnx, integrate from xn to infinity. We are taking very thick diodes, so we are integrating from here all the way up to infinity. And so we get a charge like this here. Q Ni square over Nd exponent QV by Kt minus 1 into Lp. This is what? There is excess hole charge here. Compensated by excess electron charge here, but they are there. They are distinct charges here, holes and electrons here. All right, so this is what I'm trying to tell you. Let's focus on the hole charge. There is an excess hole charge here. Now, and there is an excess electron charge also there. And the two are balancing each other. Right? So, it's overall, the region is neutral. But it's going to give rise to a capacitance. Why? Well, if I increase my voltage now, what will happen to this charge? Excess hole charge has to increase, because remember what? Qp goes as exponent QV by Kt. So if I increase my voltage, this charge has to increase, right? So let's increase this. The charge will become, instead of Qp, Qp plus delta Qp. Where has this charge come from? Well, it will come from here, right? The charge has to come from here. But along with that, remember this whole region is neutral. So what has happened? Excess electrons have also increased. Where have they come from? They have come from here. Right? So the region is neutral. Region is neutral, but I have excess holes here. So a current has to come and supply it. I have excess electrons here. The current has to supply it. So from an external circuit, what does it look like? It looks like a capacitance. I have to supply positive charge from one terminal and negative charge from another terminal. Right? So it's just like a capacitance. If now I decrease Vf here, this charge has to decrease, go back to Qp. What will happen to the holes? The holes will go back here. What will happen to the electrons? The electrons will go back here. So it's just manifesting itself as a capacitance. And therefore, what I have is a capacitance which is del Q by del T. Note that there will be a current. A current has to come in and supply this excess holes here. And this is del Q by del T. This charge here. Okay. Similarly, what about del Q1 by del T? It is this charge here. As I change voltage, this excess electrons have to change, and there will be a charge corresponding to that. There will be a current corresponding to that, del Q1 by del T. Right? So note now, in a PN junction, I have depletion charge, which we have a junction charge, which we've already talked about. We have excess holes here. And as I change voltage, it has to increase, and a current has to come in to supply that. This is this one here. Similarly, I have excess electrons here. As I increase, remember, excess electrons have to be compensated by excess holes here. So as I apply voltage, Qn increases. Along with Qn, the holes have to increase here. And therefore, they have to come from here. And therefore, I have this particular term. And therefore, now, many times, what is very confusing for people is that I have holes here, but they say the region is neutral. And neutral region, well, overall is neutral, and therefore, you have no charge. I mean, it should not contribute to capacitance. But it's a flawed argument, because if you look at depletion region also, overall is neutral, right? A positive charge, negative charge. Overall, any capacitor is neutral. A positive charge on one plate, negative charge on one plate is overall is neutral. All right. What is a capacitance and how it gives rise to current is that positive charge comes in from one side and negative charge comes in from other side. If both were coming from same side, of course, then there is no current. But positive charge comes in from one side here, negative charge comes from one side here, and it doesn't really matter You don't need a physical separation between the charges here. QP and QN are right there at the same place. It doesn't matter. Okay. All that matters is if you want to increase this particular charge here, as you increase voltage, charge has to increase. Holes have to come in from here. Electrons have to come in from here. And this is a displacement current. If you don't change voltage, well, the charge is not changing, and I don't have this current here, del Q by del T. Okay, so in addition to junction charge, I have del Q by del T and del Qn by del T. These are two additional charges in forward bias here. And QP and QN is what we call as diffusion charge. They have come in because of an injection process, and in injection after that we know this diffusion recombination. So we call this excess holes here and excess electrons here. We call them diffusion charge, and therefore when we take their derivative, so when I take del Q by del T, if I look at these two terms here, del QP by del T, del Qn by del T, I will get a diffusion capacitance. Okay, so the first term gives me junction capacitance Cj del Vj by del T. The next two gives me diffusion capacitance here. So diffusion capacitance we define as del by del Vj Qp plus Qn. Excess hole charge here, excess electron charge here. The two together give rise to a new capacitance, which we call as the diffusion capacitance. Okay, so now we have expressions for QP and QN. We can differentiate it and get their value. Okay, so again, we are making a quasi-static assumption. We are saying that the hole density, electron density goes like this here. We've obtained QP is given by this expression after integrating the hole density here. Similarly, we can get QN after integrating the electron density here. So we get total charge here. So we sum them up. We sum them up, QP plus QN. That's the total diffusion charge. We take its derivative. All right. So so this is the expression for conduction current. And what I'm trying to say is that the diffusion charge is related to the conduction current. Q diffusion is related to J0. It's easy to manipulate these two equations here and show that diffusion charge is equal to J0 multiplied by some tau effective. Tau effective is given by here. Okay. Note that diffusion charge increases exponentially with voltage. Current also increases exponentially with voltage. The rest of the terms are constants. The rest of the terms are constants, and the constants then Q diffusion come out to be a tau effective. Tau effective is given by here. You can verify that this has units of time. In the special case where tau P is equal to tau N equal to tau, tau effective is nothing but tau here. They all cancel each other. The equation simplifies to recombination lifetime. So diffusion charge is equal to the current multiplied by recombination lifetime. That's the amount of diffusion charge which is there. And now you take its derivative with respect to voltage and you'll get the diffusion capacitance here. So diffusion charge is here. Let's take its derivative with respect to voltage. So tau effective is a constant. So we get del J0 by del V, which is nothing but Q by KT J0. J0 is the conduction current. So diffusion capacitance, then we have obtained an expression is Q by KT J0 times tau effective. Okay, that's my diffusion capacitance. And depletion capacitance we have obtained earlier. So these are the only two capacitors which are there in a PN junction. Depletion capacitance coming from junction charge, diffusion capacitance coming from excess holes and electrons. All right. Okay, so this is a, all that I wanted to show through this is diffusion charge is QP by QN. J0 we have already derived, which is shown over here. And what I wanted to show you is that J0 through manipulation of equations, one can show is equal to QP by tau P plus QN by tau 1. QP is this part, LP by ND. QN is this part, LN by NA. So if we use these definitions of QP and QN, one can show that conduction current is QP by tau P by QN by tau 1. And, eventually what I wanted to write was that total current, which is this current plus del Q by del T, can be written as QP by tau B, QN by tau N, del Q by del T, del QN by del T, and all that. This is when you write currents like this is what you call as a charge control model. Everything is written in terms of charge rather than in terms of voltages and all that here. Okay. All these semiconductor devices that you will see, they all operate, almost all of them, they all operate on the following principle. You apply a voltage, and what does the voltage do? Voltage changes the charge inside the device. And as the charge changes, the current changes. So the root, voltage affects current, but how it affects current is voltage affects the charge and charge affects the current. Okay, and therefore this charge control models are very useful. They provide insight into, they show how current depends on charges themselves. Anyway, so that's on the sidelines, but let's look at an example here. So let's look at an example. So we have a PN junction diode that we have been doing. Same example, we've been looking at it to look at various aspects. Doping is the same. D and dP are given. Tau and tau p's are given here. So for this, one can calculate VBI 0.78 volt here. One can calculate current. I'm looking at only larger currents, so ignoring the recombination part. We have also derived this particular one here. And at 0.6 volt, this gives us a current of 0.185. Let's calculate the capacitance. The capacitance, we have obtained an expression Q ES 2 VBI, ND, NA plus ND. So all I have to do is plug in NA, ND, which is the same. And VBI also, we know 0.78. So it gives us a capacitance at zero bias, which is 51.5 nanofarad per centimeter square. This is capacitance per unit area. Now, if I want to calculate capacitance at 0.6 volt, well, I need to use Cj equal to Cj0, square root 1 minus Vj by Vbi. So I put Vj equal to 0.6, Vbi is 0.78. So it comes out to be 107 nanofarad per centimeter square. Okay, so you take the area, multiply it, and you'll get the overall capacitance. That's at 0.6 volt. This is at zero bias. What is the other capacitance? The diffusion capacitance, especially in forward bias. So let's calculate the diffusion capacitance. Diffusion capacitance is Q by Kt. So Kt by Q we know is 26 millivolt. J0 is this current here. And tau effective, because we have taken tau n equal to tau p, so tau effective is 0.1 microsecond. So if I plug in here, diffusion capacitance comes out to be 710 nanofarad per centimeter square. And the reason why I'm putting all this is to show you that when you forward bias, 0.6 volt is not a very high forward bias, you know that. So even at 0.6 volt forward bias, diffusion capacitance is 7 times the depletion capacitance. So in forward bias, the capacitance which dominates your behavior is the diffusion capacitance. In fact, what I've also done is, the moment you go to 0.65 or 0.7, the current is going to increase exponentially. And therefore, your capacitance is going to increase exponentially. But what will happen to this term? This term is not going to increase that much. Okay, so this term is not going to increase that much. This is going to increase exponentially here. So this is going to become even larger as compared to this. Right now, it's only a factor of 7. Is going to become a factor of 50 or 100 times more significant as compared to junction capacitance. Not only that, I've taken a particularly small value of lifetime, 0.1 microsecond. Lifetime can easily be 1 or 10 microsecond. So if lifetime is 1 or 10 microsecond, you can imagine that this tau effective changes here, and therefore C diffusion again becomes larger here. So through all these calculations, what I'm trying to tell you is diffusion capacitance in forward bias is much, much larger than the depletion capacitance. That's the significant capacitance that is there. So in forward bias, as a first order approximation, you can even forget about Cj. And you can say that my diode is basically a current in parallel with a diffusion capacitance. Okay. I have a couple of other, comparison with simulation results, but I'll skip that. And so in forward bias, as I said, you can think of a diode as a current source with two capacitances, Cj and C diffusion. And you can even forget about Cj. You can only think of current as I naught equal to Is exponent QV by Kt minus 1. And C diffusion is Q by Kt I naught into tau 0. In models, when you go into microcap and SPICE, they don't call it lifetime, but they have a specific name. They call it transit time. Okay. So in the model, this time that you see here, we tend to call it transit time. Okay. And so this is the model that we have. Now, what do we do with this model? Of course, now once, as a device engineer, you develop a model and then you pass the model on to a circuits person who will take it and use it to design circuits and all that here. But what I wanted to talk about is at the level of device, every semiconductor device has a speed, an upper limit on how fast it can operate. Every semiconductor device, whether I take PN junction diode, a bipolar transistor, MOSFET, or whatever, there's an upper limit on how fast upper limit on the operational speed of the diode here. So what do I mean by speed of the diode? So we are saying the diode looks like this here, right? Now, diode looks like this here. Now, quantifying speed can be done in two different ways. In one of them, what we do is, from this particular model here, we derive a small signal model. Right? Small signal means what? For incremental changes in voltage, how does the current incrementally change here? And you know that if I have I naught equal to Is exponent QV by KT minus 1, this component here in a small signal model translates into a resistor whose value is KT by Q I naught. And capacitors remain the same, so there's no difference here. So if I build an incremental model, a small signal model, the small signal model looks like this here. So one way of defining speed is by going towards a small signal model here and then finding out when is a diode behaving as a diode. So the idea is as follows. Whichever application you think of, when you're using a PN junction as a diode, what you're doing is you're relying on this current I naught. In forward bias, you want I naught to be high. With very little voltage drop, you want the current to be high. And in reverse bias, you don't want anything to flow. That's the property that you're relying on. But then, besides I naught, what else do you get? You get a capacitance. So any current which flows through the capacitance is in fact something that you don't want normally. You want this current. You are interested in this part here. Anything which flows through here is an unwanted component. Okay, it's an unwanted component. And when significant current starts flowing here, it begins to distort your characteristics. Your characteristics, you want it to be dominated by I naught. That's the diode here. That's what causes rectification. It's not this here. In fact, this is something that you don't want. You don't want this, you don't want this here. So in small signal terms, what does it mean? That if I want current to flow through RD. I want current to flow. RD is coming from this one here. So when I'm using under small signal condition, I want my current to flow through RD. I don't want it to flow through C diffusion and CJ. The moment the current starts flowing through capacitances, the diode is no longer behaving in a familiar manner. Okay, so that's the idea. This is what is limiting the speed. When currents start flowing through capacitances, you know that it's no longer behaving in a proper manner here. You want current to be determined here through this. Because remember, rectification is coming due to what? That current in forward direction is different from reverse direction here, right? But what about a capacitor? Capacitor is, equally well in both directions. Whether I apply a positive voltage or a negative voltage, it flows in both. So it destroys your operation here. So how can I define speed of the device here? If I look at this one, what would be a good way of defining speed? How fast can your diode operate? You want current to flow only through here. But now suppose, neglect CJ. In forward bias, CJ is small. Now some current is flowing through this also. So how do you define speed now? That this current should be much, much smaller than this. So what will be the threshold point? Impedance? Much larger. Impedance of the same thing, impedance of the capacitor in terms of sinusoidal steady state, impedance of the capacitor should be much larger than RD. Now, up to what point can you say your diode is working okay? When the impedance here becomes comparable with this, you can say then, well, you can't use beyond it. No? 10 times, okay. So in this case, what I have said is maximum highest speed that you can operate your devices when this impedance, you're right, this impedance becomes comparable with RD. Well, you're right. You can say this impedance is maybe 10 times RD. To be on the safe side, you can say 10 times RD. I have no arguments with that. You can put anything like here 10 times for 5 times. But then what does it tell us? What is the upper limit on the speed of operation defined in terms of frequency? F max is 1 over 2 pi tau naught. What determines the speed of your diode? Tau naught. And what is tau naught? Recombination lifetime. The recombination lifetime determines the speed of your diode. For a thick diode here, this is a very important point here. For a diode with thick P and N junction, that's the diode that we have been looking at. Tau 0 is nothing but recombination lifetime. How fast your diode operates depends on this tau naught. Okay. Now, the arguments that I've used to calculate the speed, the same arguments are used to calculate the speed of a bipolar and a MOSFET. You go to a small signal model, and a small signal model, what do you want? You want current to flow through resistive parts. You don't want current to flow through capacitive parts. The moment the current through capacitive parts becomes comparable with this, that's the upper limit of frequency. Your device is no longer behaving properly, and you get an upper limit there. That's it. Okay. So all you need to do is find out the resistive parts, find out the capacitive parts, equate the currents, and you get an upper limit on current here. Yeah. Thin.
And the width is lesser than the predicted.
Yeah, that's an interesting case. We'll do that. That's what happens in a bipolar. Bipolar transistor widths are very thin. Okay, so that's an interesting case. It no longer depends on recombination lifetime. It depends on how thick, what the thickness of P and N regions are. Okay, so we have to redo the current and all that, because remember, diffusion capacitance is related to current. So we have to recalculate the current expression and show what happens there. Okay, so we'll do that as a special case here. So now the speed of the diode depends on the recombination lifetime. All right. So now it brings in the other way of calculating speed is not through small signal, but what you do is you look at large signal response. And this is something that you have done in your 380 experiment. So what you do is you take a PN junction, you have a resistor, you apply a forward bias. When you apply a forward bias, some forward current flows. Suddenly you switch it to reverse bias here. The current doesn't drop to zero. The current goes into negative because the diode is still on. The current continues to flow and then drops to zero here. Right? So from a diode's property, the moment you reverse bias the voltage here, you would have expected the current to go to zero here. It doesn't go to zero. It goes to zero after a certain time, which we call as the reverse recovery time. Right? So this is a measure of the speed of a diode. The diode is remaining on even when you reverse bias it for this extra time here. Right? Extra time here, and that's a measure of the speed. Tau RR. And using this model here, using this particular model here, I naught and C diffusion, one can show that the reverse recovery time is also tau 0, ln 1 plus IF by IR here. So again, it depends on tau 0 here, recombination lifetime. I'm not going to go into the details of this derivation here. We'll leave it as a homework problem. So even in the large signal response, I get a recombination lifetime, which is limiting the speed of the diode here. Okay.